Hello again. Well, when I left off, I guess it was yesterday, I'm pretty sure the last thing I covered was about unit vectors. So far, all I've talked about is addition, how to add a vector to another vector. Let's get into at least some other operations. First of all, multiplication. For now, we're just going to do multiplication of a vector by a scalar. Multiplication of a vector by another vector is something we will cover in this course, but that's going to wait until another day. So basically, well, first of all, if you want to think of it in terms of pictures, it works like this. By the way, if you notice my fingers are a little on the purple side, I've been picking elderberries. Anyhow, if you've got some vector, we'll call it V for vector. If you want to multiply that by 2, I'm just going to kind of eyeball this. That looks about twice as long. Or 3 times V would be 3 times as long. Negative reverses it. Negative V, which should be the same thing as negative 1 times V. Negative 2 times V would be like this arrow, except the arrowhead would be on the other end, and so on. 1/2 V, as you probably guessed, is half as long as that, and in the same direction. But this is the same thing as a vector divided by a scalar. Just like with regular numbers, 1/2 times V is the same thing as V divided by 2. So multiplication, and for that matter, division by a scalar, keeps the vector parallel to its original direction, but changes scale, which I don't know if that's where the word scalar comes from, but I'm suspicious. If you want to think of a vector as a collection of components, rather than thinking of the vector as an arrow, n is a number, a scalar, times vector V, well, you just multiply each component times n. Maybe I'll write it like this: n times Vxi plus Vyj plus Vzk, if it's a 3-dimensional problem. And it's just the distributive property. Okay. So if you think of a vector as an arrow and you multiply it by 2, you make the arrow twice as long. If you think of a vector as being a collection of components, then if you want to multiply it by 2, you multiply each component times 2. So now, armed with all this knowledge about how to do vector, or oh, one more thing. Subtraction. If you're talking about scalars, Subtraction is just a variation on the idea of addition. 4 minus 3 is the same thing as 4 plus negative 3. And it's the same thing with vectors. A minus b is a plus negative b, where negative b means turn it around like that. So head to tail vector addition with the negative of the second vector, that's how you would subtract. Um, so as examples of this, yeah, where do I have that written out? I've got the wrong page sitting next to me here. Hold on. No, I don't have the wrong page sitting next to me. I'm doing things in the wrong order. I had skipped over example number 4. So that's next. There's some object here, could be coffee cup, which I probably ought to wash. And if there's 3 strings tied, well, some tape, okay? There's a string tied to the cup or taped to the cup that somebody's pulling that way with a force of 6 pounds. And another one that somebody's pulling that way with a force of 4. And a third person over here has a third string and they're pulling it that way with a force of 9 pounds. And the question is, what one single force would have the same effect on the coffee cup as these 3 acting at the same time? And as we've already seen, one way of answering that question is to do the scale drawing where they're all laid out head to tail. But I want to calculate it this time. So there's actually more than one way of calculating the resultant of some vectors. But by far the most versatile is to use the method of components. Okay, so much so that I'm not even going to bother mentioning. I mean, if you're really curious, ask me sometime. And well, actually, it takes like 10 seconds. But if you've got a couple of vectors, one like that and one like that, and you need to figure out r and theta. Another way of doing that, aside from the method of components, is you've got this triangle, you can use the law of sines and the law of cosines to find r and theta, okay? But that's fine when there's only 2 vectors. If you've got 14 of them, this becomes incredibly cumbersome, and we won't even try and talk about doing this in 3 dimensions, whereas the component method, if you've got 14 vectors to add, it gets kind of time consuming, but that's it's a lot more versatile. So that's what I'm going to use pretty much exclusively. If you're going to use the component method to find the resultant of some vectors, probably no big surprise. The first step is to find the components of each vector. Just like I did in example number 3 here, okay? It's just like doing example number 3 over and over again. Do it for this vector, do it for that vector. If there's 14 of them, you just keep doing it over and over. So step 1, find the components. Take each vector one at a time. Don't be distracted by the others. I recommend a separate picture. I mean, honestly, how long did that take me? You know, you can afford to draw a picture. So there's vector A. We know that it's got a magnitude of 6 pounds, and I'll fill that in at some point. 30 degrees from the x-axis. It has components that I'll call AY and AX. And as we saw in that earlier example, AX is equal to A cosine of 30 degrees. Hypotenuse times cosine is the adjacent side. We know that A, the magnitude of vector A, is 6 pounds. The cosine of 30 is approximately 0.866. Your calculator will keep going, but I don't feel like writing all that down. And that times that is 5.20. As for how the units work, trig functions, really any kind of transcendental function, gives you a dimensionless number. Okay, the 0.866 is just a number with no unit on it. So you've got pounds together with nothing else gives you pounds. Same kind of story with the y component, except that you use sine. Sine of 30 is exactly 1/2, so this comes out 3.00 pounds. And so vector A in unit vector notation, 5.2, I'm going to be lazy and leave off the 0, but I really ought to include like I did over there. Same thing here. Next vector, do the same thing again. We have vector B. Where this is 4 pounds and this is 60 degrees. So just like before, hypotenuse times the cosine of the angle gives you the x component. Hypotenuse times the sine of the angle gives you the y component. There's our second vector. And the third one, another picture. That one points right straight to the left, right down the negative x-axis. And it's, well, really the only thing that's worth writing down is minus 9i. The negative sign because it points to the left. And if any of our y components had pointed down, they should be, because see, the next step is going to be to add things. And when you put them together, things with opposite directions have to cancel each other. So to get them to cancel each other, opposite directions have to get opposite signs. So all that really matters is opposite directions have opposite signs, but the usual way of doing things is to make negative be left and down. Anyhow, minus 9i is all you really need, but just to be really thorough for the first time through something, I'm going to go ahead and write down that the y component is 0. And if there's 14 vectors instead of 3, you just keep doing that over and over and try to stay awake. So once you have everything in terms of components, step 2, add. The resultant, I thought the letter R might be a nice name for the resultant. It's the sum, the vector sum. A plus B plus C. And of course, where people go wrong, even into Physics 132 in the spring, is A plus B plus C. 6 plus 4 plus 9. That's 19. No, A is not 6. 6 is a scalar. A is this vector, 5.2i plus 3j. And B is this vector, 2i plus 3.46j. And this one is C. And then when you do algebra with vectors like this, it obeys all the familiar rules from when you learn to do scalar algebra. It's commutative, it's associative, the distributive property, all that stuff. The fact that I and j are vectors instead of numbers makes no difference. You handle them in the same way. So the thing to do here is to collect the like terms. Put all the i's together, put all the j's together, and then factor out the common factors. So 5.2 plus 2 minus 9. Okay, so distributive property. 5.2 times I, like I've got there, 2 times I, like I've got there, and minus 9 times I, like I've got there. And then same thing with the y components. And again, it's not really worth it writing down 0, but I just wanted to make the point that the way you add vectors by using the component method is that you add up the x components of each vector to get the x component of the resultant, and you add up the y components of each vector to get the y component of the resultant. So it probably says that here somewhere. No, it doesn't. But, well, I'll write it down here in a moment. Just to get the answer written down, first of all, the resultant, the answer to the question, is negative 1.80 I plus 6.46 J. Don't forget the unit. This is measured in pounds. It's a force measured in pounds. So to summarize what happened there, so the camera's aimed too low for up there. The moral of the story is the resultant's x component is the x component of the first vector plus the x component of the second vector plus the x component of the third vector plus, you know, if there's 14 of them, however many you add them up. And The y component of the resultant is ay plus by plus cy, however many of those there are. And if it's a three-dimensional problem, it would be the same sort of thing with the z components. The method of components generalizes very easily to three, well, I shouldn't say that. There's nothing trivial about jumping to 3 dimensions, but as far as the underlying idea, anyhow, you just write this one more time. The z component is az plus bz, and so on. Now, expressing a vector as a set of components is a perfectly legitimate way to describe a vector. Okay, people do it all the time. For certain purposes, it's the most convenient way of doing it. But for other purposes, you might want the magnitude and direction. So the way this question is phrased, where it says, find the resultant, well, with a question phrased that way, you can call this the answer, and you'll get full credit for that. But if I had slipped in just a couple more words, if I had said, find the magnitude and direction of the resultant, then there would be one more step. So 3. If the r theta form, the magnitude and direction, is needed for the answer, instead of expressing it in using the xy approach instead, well, the first thing to do is draw yourself another picture. Okay, keep saying, don't skimp on the pictures. So the x component came out negative. So it points to the left. And the y component came out positive. So it points up. And x was 1.8 to the left, and y was 6.46. And the vector that we're trying to determine is the resultant of its x and y components. So you do the usual head to tail thing. You're adding, like it says right there, you're adding negative 1.8i, which I've drawn here, to 6.46j, which I've drawn here. And vector addition means this head to tail process that I've sketched. So we want to know what's r and what's theta. Well, we're going to get r from the Pythagorean theorem. So r is equal to the square root of that, which is about 6.71 pounds. As for the angle, well, this angle in here is the arctangent. Actually, the more common notation for the inverse tangent is to write it like that. I think that's probably the more common one. But I've never cared much for that, because at least with introductory students, they're always thinking that when you raise something to the negative 1 power, that's a reciprocal. And That is not what this means. It means the inverse function. Well, if you use this notation, people aren't tempted to think that. But anyhow, it's just two alternate notations. If you're used to this, well, you're in good company. A lot of people are. Anyhow, opposite over adjacent. 6.46 over 1.8. So you divide, you go second function tangent on your calculator, and it comes out, looks like 74 degrees. So the angle measured from the positive side of the x-axis would be 180 minus 74, which is just a little under 106 degrees. And so the answer expressed this way, instead of in terms of x and y components, is 6.71 pounds at 106 degrees. So there you go. That's how you add vectors using the component method. And I already said the thing about how to do vector subtraction. So we've got an example coming up that'll illustrate subtraction. And I'll go through that with you right after I pause this briefly. Okay, an example of where subtraction of vectors comes up is in the definitions of velocity and acceleration. Okay, velocity, for example, means the change in the displacement, or change in your position over the change in time. And in section 1, where things always stayed on the x-axis, that was just subtracting two numbers, x final minus x initial. In 2 dimensions, it works like this. So let's say there was a mosquito flying around in here. And at one particular moment, this here, the origin is some convenient reference point that I've chosen, and x means horizontal and y means vertical. And at some particular moment, the mosquito is there. R for radius, the radius vector out from the origin to where the mosquito is. R1. And a little while later, maybe just half a second, now the mosquito or you know what? I really don't like mosquitoes. Let's make it a firefly. So now the firefly is over here. Fireflies are cool. Mosquitoes are nasty. They bite you, they spread malaria. Delta R, okay, maybe I should, velocity is the change in the position over the change in time. It's going to be delta R over delta T. Delta R is this vector here from where the firefly was to start with to where it is in the end. Okay, points from the initial to the final position, delta R. And as always, delta means final minus initial. R2 minus R1. And the subtraction of vectors means to add the negative. So just to make a sketch, if you've got R2, that looks like it's about that long. Here's some real precision measurement for you. It goes to there on my finger. A little longer. More like that. Okay. So there's R2, and we're going to add that head to tail with negative, it should be a little steeper, kind of, sort of like that. Okay, I tried and probably failed to draw that at the exact same angle as I drew it over here, but I stuck the arrowhead on the other end. R1 points that way, negative R1 points the other way. Add head to tail, R2 and negative R1. The resultant goes from the tail of the first vector to the head of the last one, which is the same thing that I drew over here. Okay. So velocity instantaneous velocity would mean that you have to let the time, t2 minus t1, the time to get from one point to the other has to approach 0. Which can be written more concisely like that. Okay, so generalizing the idea from one-dimensional motion, the derivative of your location is the rate that your location is changing. In other words, is your velocity. And what dr means is it's an extremely small delta r, and what delta r means is R2 added to negative R1, final minus initial. Okay, and of course, it's the same story pretty much all over again for the definition of acceleration. If our Firefly has an initial velocity maybe sort of like that when it's there, and a final velocity, I don't know, maybe sort of like that when it's there, then delta V would be V2 added to negative V1. So let's see if I can draw them the same way again. That's probably passable. Negative V1 and so delta once again means final minus initial. Subtracting vectors means to add the negative. The negative means turn it around and point it the other way. Add means put them head to tail and then draw the resultant. And acceleration is delta V over delta T in the limit where the time approaches 0, which can be written more concisely as, using a D to stand for an infinitesimal. Delta means some finite interval. And let me point something out that will be significant in a week or two. Notice that, I mean, I drew this so that this arrow was a little bit longer than that one. Firefly picked up a little speed as it was flying along. But even if these were the same length, okay, just if V1 was a little bit longer, it would just tilt the resultant a little further over that way. But if this insect is going 4 miles an hour to begin with and still going 4 miles an hour in the end, notice that delta V is not 0 because of the difference in direction. And if delta V is not 0, the acceleration is not 0, okay? So something is accelerating when there's any kind of a change in velocity, speed, or direction. Even if the speed doesn't change at all, like if you're in your car, if you're driving on a curve, you're accelerating, even if you've got the cruise control turned on. So we'll get back to that in, I think it's section 4. For now, example. We're going to kind of anticipate Newton's second law, which is going to be pretty much the first thing in section 3. But the question tells you that force equals mass times acceleration. And it tells you the mass of some object and tells you its initial and final velocity and the amount of time that passes in between. So from the change in velocity over the change in time, you can get the average acceleration. Okay, if you need an infinitesimal time to get instantaneous acceleration, but for average acceleration, you can use 3 seconds and it'll give you the average during that 3 seconds. And once you know A, you multiply it by the mass. So this makes use of subtraction and it makes use of multiplication by a scalar and all that stuff I was talking about further up the page. Here goes. Now I got the camera pointed too low. Part A, acceleration, average acceleration. If it's got deltas, it's the average. If it was instantaneous, they'd be D's. Delta V means V final minus V initial, and both of those were given in the question. Final velocity was 2I minus 2J. And the initial velocity was 5I plus 7J. The amount of time that passes between having this for the velocity and having that for the velocity is 3 seconds. Okay, well, if you put the two I terms together and then factor out the 2 and the negative 5, maybe I should write that out. You've got 2 times I here, and you've got negative 5 times I there. And you've got negative 2 times J there. And don't forget to distribute the minus sign. I know you all know better, but that doesn't stop people from doing it. So, I mean, everybody has bad days, but negative 7. So distributive property, factor out the I from those two terms, Factor out the j from those two terms. So we've got negative 3i and negative 9j. So in the first term, 3 divided by 3 is 1. And in the second term, 9 divided by 3 is 3. And this would be measured in meters per second per second. That's the answer to part A. That is the acceleration vector in component form. Part B. Force equals mass times acceleration. They tell us the mass is 5 kilograms. And the acceleration is the answer to part A. Vector times a scalar. It's just the distributive property. 5 times negative I, 5 times negative 3j. And as I will explain fairly early in section 3, kilograms times meters per second squared is called a Newton. For sort of a temporary definition, well, more of an explanation than a definition, really, but a Newton is a metric unit of force, which, if you're not being too terribly precise, a Newton is approximately equal to a quarter of a pound. A stick of butter weighs about a Newton. More on that in the next recording. Part C, find the magnitude of the net force. Well, this vector here is the net force, and part C says, what is the magnitude of that? Well, from someplace near the end of the previous recording, you get the magnitude of a vector from its components by using the Pythagorean theorem. I probably still got that laying around on the floor down here somewhere. Unless I don't. Yeah, well, it's on the formula sheet. Guess I cleaned up after myself a little more recently than I thought. So the x component is negative 5, and the y component is negative 15. But I didn't really need to bother writing down the minus signs because they go away when you square the thing. And 15.8 newtons. I should probably make a point at this point, which is that the magnitude of a vector is always a positive number, okay? I don't care if the components are negative. Magnitude is to a vector what absolute value is to a scalar. It's, well, the alternate notation is, instead of just writing the letter F, I could use absolute value signs. So magnitude is positive by definition. It's just how long is the arrow. I don't care which way it points. That's a positive number. So There's no such thing as a negative magnitude. I've got one more problem, and then that's the end of section 2. So this is a little bit like the lab you do in section 2, where there's a metal ring and there's 3 spring scales calibrated in newtons. But in the lab, you start out knowing all 3 forces and you're trying to determine the total. Here it's the other way around. You start out knowing only 2 of the forces and you know the total. So you work back from the total to figure out what the third force must have been. And the reason that you know the total of all these forces is the question tells you that that ring is at rest. For an object to remain at rest, the total force on it has to be 0. An object can only stay at rest with no net force on it. So the resultant of these 3 has to be 0. Writing that as an equation instead of in words, vector A plus vector B plus vector C. Well, if you really want to nitpick about terminology, technically 0 is a scalar. I guess this would more properly be called the null vector, but people hardly ever do. So fill in what we know, solve for what we don't know. Vector A is 5 newtons pointing right straight down the x-axis, 5 times I. Vector B is 3 newtons pointing right straight up the y-axis, 3 times J. And vector C, that's what we want to know. Well, as I've already mentioned, vector algebra works just the same as the scalar algebra. Since it's not the same thing, it is worth taking a moment to say so. And, you know, you get deeper into this stuff, and actually things do start to get a little strange, because like when you get into multiplying vectors, the cross product is not commutative. A cross B does not equal B cross A. So it is worth mentioning when you can use the familiar principles from working with scalars. But for something like this, everything you're used to, you know, you solve it the same way you would any equation. We're going to subtract 5i from both sides. We're going to subtract 3j from both sides, just as if it was an equation full of scalars instead of vectors. So when you do that, what's left to the left of the equal sign is just vector c. You know, as usual, the goal is to isolate the variable. C equals and that was measured in newtons. And the question doesn't specify that we need the magnitude and direction, so since the components are the first thing we got to, we might as well leave it that way. And that is the third force that's needed to balance the other 2. And that wraps up that one. Have a good rest of your day.